Just
Yeah,
post
it. I want to see who from the program is going to do the introductions. And I'll just make a quick introduction to is Shihab is just joining. There we go. I'll give colleagues a couple of minutes to continue joining.
Sure.
And I'll be here, but I'll probably stop my video and mute myself and make sure that we're not dropping things in any of the balls. All right, I think we have we might, let me see if we can get started. And I'll turn it over to you in a second, Xiaohang. I just want to make sure. Oh, okay. I thank you very much, Xiaohang, for being patient. I just wanted to make sure that I'm the only one that is making a quick introduction. So welcome everybody for the public promotion colloquium of Professor Xiaohang Li. Xiaohang is a candidate for promotion from assistant to associate professor of electrical and computer engineering. He has been with us with a number of years and doing all sorts of great things on developing new materials with applications in energy and in energy systems and in lasers. So without further ado, I'd like to turn over the floor for Xiaohang for the promotion colloquium. And Xiaohang, the floor is yours.
Yeah, thank you very much, Dean Omar, for your kind introduction. So let me share my screen. Can you see the screen well?
Yes.
Okay, thanks.
Yes.
So yeah, thanks again for the introduction, and thank you so much all for being here today. It's my great honor and privilege to talk about our research, particularly on the ultra-wide bandgap semiconductors. So just a quick background of myself. So I got a PhD in electrical engineering from Georgia Institute of Technology in the summer of 2015. And then in January 2016, I joined KAUST as an assistant professor of ECE and later associated with applied physics. My teaching and research interests include semiconductor materials, devices, and physics, in particular based on the ultra-wide bandgap semiconductor for optoelectronics and electronic applications. Here are my scholarly outputs and several of the awards I have received in the past. So since the COVID-19 began early last year, there was a great shortage of facial masks all around the world. The prices of the facial masks went through the roof last year for a long time. And however, if you look at the news since early this year, the headlines has been taken over by the shortage of semiconductors and semiconductor chips. The shortage of semiconductor has stopped the production from computers to cars, vehicles, and it has inflated the prices of almost everything using electricity. So this shows that the semiconductor chips are really the physical brain of almost everything in the information age today. So let's talk about semiconductor. So there have been 4 waves of world-changing inorganic semiconductor in the past based on a key property, which is called bandgap. The bandgap is the shortest energy distance for a bound electron to become a free electron so that it can conduct current. It is perhaps the most consequential property of semiconductors. And for metals such as copper, aluminum, gold, and platinum, there is no bandgap, or the bandgap equal to 0. So the bound electron can become free electron very easily, and therefore the metal has the highest conductivity out of all the materials we know today, except a superconductor. And but for an insulator, which does not conduct any current, the band gap can be very, very large. And because of this large band gap, the bound electron cannot gain enough energy to become free electron to conduct current. And semiconductor is somewhere between the metal and insulator. So for the electrons as bound electron in the semiconductor, they could gain enough energy, some of them could gain enough energy to become free electrons. And people can introduce additional techniques such as doping to enhance or decrease the conductivity of the materials. Therefore, this is the fundamental property of semiconductor. The first wave of semiconductor is silicon and germanium. They have a band gap about 0.7 and 1.1 electron volt. Electron volt is an energy unit to describe quantum mechanical particles and electrons and holes in different materials. So some of the greatest inventions based on silicon and germanium include the invention of transistor and integrated circuits. And nowadays, the silicon-based integrated circuit really play a central role in the human society, from electronic computation, data storage, graphic processing, power management, MEMS, and the photovoltaic technology on the Earth's surface. The second wave of semiconductor is so-called 3-5 semiconductor. Basically, it comprises elements from group 3 and group 5 from the periodic table. Those materials include gallium arsenide and indium phosphide with a larger band gap, about 1.3 electron volt. But in addition to having a larger band gap, those materials have a direct band gap as well. So this means that they can be made into LEDs and lasers with high efficiency, emitting at the wavelength corresponding to their band gap energy. And nowadays, they have been made into lasers that power the global internet. And also, we can find those lasers in our iPhone for the facial recognition and the LiDAR system for autonomous driving. In addition, they can be used in the solar cells commonly seen in space. In addition, those materials have very high electron speed. This means that electron can move very fast in those materials compared to silicon. And therefore, they have led to some of the fastest devices used in the GPS system in our cell phones these days. The third wave of semiconductor is the so-called wide bandgap semiconductor, represented by gallium nitride and silicon carbide. They have a larger bandgap, about 3.3 electron volts. This larger bandgap allows them to have a larger breakdown field, and therefore they can handle power at very high voltage. So you can find their application in every single Tesla cars, as well as the 5G towers and high power radar system. In addition, materials such as gallium nitride have the so-called direct bandgap as well. So they can be made into efficient LEDs and lasers for the visible spectrum. So they are right now the foundation of the modern lighting and display technologies. And I believe that almost every single artificial photon on KAUST campus is generated out of the gallium nitride-based LEDs. So actually, all the three waves of those semiconductors have made the Zoom meeting possible today, right? From the computation, graphic processing, to the global internet, as well as lighting and display. So what will be the next, along this ladder? So that will be the topic of today. That is the ultra wide bandgap semiconductors. They have a much larger bandgap, up to 8.6 electron volt. They include materials such as aluminum nitride, boron nitride, as well as oxides such as gallium oxide and aluminum oxide. And because of the much larger bandgap, they can handle a lot more power compared to any material below. And that is essential to improve the energy efficiency of the human society, to slow down the global warming and enhance connectivity beyond 5G. In addition, because of the larger bandgap, they can operate in a shorter wavelength UV spectrum. And the UV photonics are crucial to prevent the future pandemics. It is also very important for sensing and deep space exploration. And also with the very large bandgap, they can serve as the host and photonic platform for quantum information science, including quantum computing. So all of this means that the ultra wide bandgap semiconductor will be indispensable for future challenges and opportunities of the mankind in the decades to come. So in our group, we have focused on the boron, aluminum gallium nitride, ultra wide bandgap semiconductors with a bandgap from 3.3 to 7.2 electron volts. So because of the infancy of the ultra-wide bandgap semiconductor research, the material growth is really the key here, because without synthesizing good materials or materials with different compositions, it is not possible to understand the potentials of those materials for different device applications. So before I get into the technical details, I would like to thank all the help and support I have received since I joined KAUST. So first of all the results are attributed to the efforts of students and researchers who have studied in my group. And also I'd like to thank all the KAUST colleagues, and including faculty and staff, and especially the collaborators listed here. In addition, I would like to appreciate the support from internal and external funding. And last but not least, core labs, LEM and EMPN have been instrumental for the development of my group. And also I would like to thank all the external collaborators in different countries as well. So here shows the bandgap versus lattice constant of the boron aluminum nitride and boron gallium nitride, along with the more conventional 3-nitride materials. So as opposed to the more conventional materials, they are highly nonlinear, as you can see from those curves here. And also they have a wider bandgap range, a direct to indirect bandgap transition. And also they can form the lattice matching opportunities with technically important aluminum nitride, silicon carbide, and gallium oxide substrates. In addition, the large variation of lattice constant can lead to opportunities of strain and polarization engineering. There are more interesting properties, which I'm going to talk about later. But all of this means new enormous opportunities for electronic and optical devices. So recently, the United States National Science Foundation has organized a workshop on the future of semiconductors and beyond. Many experts in the US have talked about their vision for further development of semiconductor technologies. In particular, Steve Danbos from UC Santa Barbara and Hui-Li Xing from the Cornell University, two leading experts in the world, have talked about their vision for the ultra-wide bandgap semiconductors. And in both of their talks, they have emphasized that the boron 3-nitride material will be indispensable for the future development of the semiconductor technologies. And since I joined KAUST, we have built an international leading research program in this emerging area through multidisciplinary research. That includes growth, materials, physics, and devices. So let's talk about growth. As I mentioned earlier, the growth of the materials is very important for emerging semiconductors. The growth of the boron 3-nitride material is very similar to that of indium gallium nitride, which is the foundation of our visible LEDs in its early days. For indium gallium nitride at that time, there was a lack of high quality epitaxial epitaxial gallium nitride as a substrate. For boron aluminum nitride and boron gallium nitride, there is a lack of high quality epitaxial aluminum nitride. The aluminum nitride chosen here to be the ideal template or substrate because it has the closest lattice constant for reduction in the strain and cracks. So in addition, for being the foundation for boron aluminum and gallium nitride materials, the aluminum nitride is also the foundation for very important devices from UV, power device, frequency device, and piezoelectric devices. And therefore, it is very important to study how to obtain high quality and low cost epitaxial aluminum nitride. So in the pursuit of high quality epitaxial aluminum nitride, people can use two kinds of substrate. The first one is the native aluminum nitride substrate. So basically it is the same material as the epitaxial aluminum nitride. So it does not have dislocation, does not have a lattice or thermal mismatch. And therefore you can have very low dislocation density, about 10 to the power 4 for the epitaxial aluminum nitride. However, this aluminum nitride substrate has significant drawback as well. First is that the size of the substrate is relatively small. Also, it's very, very expensive. And today, a 2-inch, which is a 5-centimeter diameter aluminum nitride substrate, can cost about $5,000. So if a student of my group come to me and say that, okay, I can want to buy 10 of this substrate to do research, that is a very significant portion of my annual budget. So it is not really practical for large scale application and even research in my at present. Another kind of substrate is a so-called aluminum nitride substrate. Is a sapphire substrate. Sapphire is basically aluminum oxide. And in comparison to the aluminum nitride substrate, the sapphire substrate is very, very economical. A 2-inch sapphire substrate costs merely $5. This is thanks to the high volume production of sapphire for blue and green LEDs. And however, it has its own drawback as well, because they are two different materials. They have the so-called large lattice and thermal mismatch. And this large mismatch can lead to high dislocation density, about over 10 to the 10 per centimeter square. And but we do not necessarily have to go to 10 to the 4. We just have to hit about low 10 to the 9 for decent devices for many applications. So let's talk about the material growth of compound semiconductors, especially the ultra wide bandgap semiconductors. There are two techniques. The first technique is the so-called molecular beam epitaxy, or MBE. MBE was invented by Cho and Arthur Jr. at Bell Labs in 1968. And it has become the best technique to grow epitaxial material in terms of excellent materials and interface quality. And this growth happened in ultra high vacuum. And for example, if you want to grow aluminum nitride, the aluminum atoms and nitrogen atom will subline from their solid sources and then move towards a heated substrate and then combine into a solid molecule, layer by layer on a heated substrate. Another technique is a so-called MOCVD, or metal organic chemical vapor deposition. It was also invented in 1968, what a year, by Harold Manasevich at Rockwell International, initially for radio frequency applications. And from the chemical, you can guess that this will be a chemical deposition process instead of a physical deposition process. And in this process, the precursors such as trimethyl aluminum, so one aluminum with three CH3 methane groups, in the gas phase will react with ammonia in the gas phase to generate the aluminum nitride in a solid phase and methane in a gas phase. So, as compared to other techniques, the MOCVD can lead to good quality, but also very fast growth rate and good scalability. And therefore, MOCVD has been used to produce most of the compound semiconductor devices today. It is estimated that trillions of LED chips and LEDs and laser chips are produced each year by MOCVD. So here shows a basic diagram of an MOCVD system. It comprises a gas handling system, a low loss chamber, a growth chamber, and the exhaust system. The chemical reaction happened in the growth chamber, as shown right here. So basically, under the higher temperature, the precursors, for example, like trimethyl aluminum, will decompose into atoms in the absence of oxygen, or called pyrolysis as this process. And this pyrolysis can leave the atoms diffuse on top of a heated substrate and then bond to each other to form a new crystal layer, atom by atom. Right? So it's a epitaxial process. And to grow aluminum nitride by MOCVD, because it's a chemical process, the growth is very sensitive to the initial substrate condition of the sapphire substrate. And this image here shows the high resolution TM image carried by my group down in the KAUST core lab, showing two kinds of polarities of aluminum nitride grown by MOCVD on sapphire. And this difference in the polarity is thanks to the initial substrate conditions. Ideally, we want only one polarity, especially the aluminum polarity, because aluminum polar aluminum nitride has smoother surface and better chemical stability. But without a proper surface treatment, you will end up with both aluminum polarity and the nitrogen polarities. And this is not ideal for device applications. The polarity here basically means that how the aluminum atom and nitrogen atom orient themselves, just like a dipole. So there have been many ways to treat the sapphire substrate before the aluminum nitride growth. The first way is a so-called ammonia preflow or nitridation. And the mechanism of this method is well understood. So basically, the aluminum polar aluminum oxynitride can be formed by annealing the nitrogen polar aluminum nitride after the ammonia preflow. And then the aluminum polar aluminum oxynitride will further lead to the aluminum polar aluminum nitride, which is what we want. However, another technique that is also very popular has not been well understood. So basically in this technique, people will flow the trimethyl aluminum, again, is one aluminum with three methane groups before the growth of aluminum nitride. And some researchers hypothesize that a few monolayers of aluminum atoms or aluminum-rich layer are formed during the pre-flow process. And then on top of that, if you do the growth, you will have aluminum polar aluminium nitride. However, there has been no direct evidence to support this hypothesis. And also, it will be very amazing if a layer or if a thin layer of metal can be formed between one insulator and one semiconductor, right? So we wonder if this is a real mechanism. So we want to, because this is very important to grow the high quality aluminum nitride on sapphire architecturally. So that's why we conducted 3 experiments. The first is to, do not flow any trimethyl aluminum before the growth, right? So we just grow aluminum nitride directly on sapphire. For the second sample, we flow 5 seconds of trimethyl aluminum before the growth. For the third sample, we flow 40 seconds before the growth. So different time just corresponding to different doses of molecule you deposit on the sapphire substrate for pre-treatment. And after the growth, we used the SCM to examine the surface. And as I mentioned earlier, the nitrogen polar aluminum nitride will have very rough surface. This is what we saw for the first sample without any pre-flow. And however, for the second sample, the surface is very smooth, so indicating that this is aluminum polar. For the third sample, the surface is also very rough, but this roughness is very different from the first sample because this roughness shows these mountain-like features or multifaceted feature, right? So to further verify the polarity, we use the KOH solution to etch the sample. And the KOH is very good at etching the nitrogen polar. The nitrogen polar aluminum nitride can be etched away very quickly by KOH. So that is what we saw for sample 1. So nothing was left after the etching. And for the second sample, the sample was intact, right? Indicating that this is aluminum polar aluminum nitride. For the third sample, the aluminum nitride still exists. The only difference is that all those facets were gone, right? So this shows that the sample is aluminum polar. The reason that those facets were gone is because the KOH can attack and etch away those facets very well, but cannot etch away the so-called C-plane aluminum nitride, which is the flat surface. So to further investigate this, we conducted a TEM study with the emphasis of looking at the impurities between aluminum nitride and sapphire. The impurities can include carbon. And where is the carbon from? The carbon is from the trimethyl aluminum, which is the precursor for the pre-treatment. For the first sample, we did not see any carbon, right? It is very clean. For the second sample, we start to see scattered carbon as represented by the yellow spots right here. And for the third sample, we see significant amount of carbon, as you can see here. And also interestingly, the oxygen coexist with carbon, right? You can see they have the same shape. And also this is very significant carbon. So this also means that like if we grow aluminum nitride on top, essentially we are not growing on a flat sapphire substrate, but we are growing on a very rough with different carbon islands. So it's like a growth mask. But the coexistence of oxygen and carbon indicates that the carbon has captured the oxygen, which actually prevent the formation of nitrogen polar aluminum nitride. So based on our study, we have proposed a new model to explain and use the trimethyl aluminum treatment of sapphire substrate. And we note that the carbon from the trimethyl aluminum is the key here. And for a sample without any carbon, we will have this blue color nitrogen polar aluminum oxide nitride. And if you grow on top of it, you will have this very rough nitrogen polar aluminum nitride surface, which is not good for device applications. And for the second sample with a proper amount of carbon, right, with scattered carbon, those carbon can attract oxygen from the sapphire to avoid the formation of aluminum oxide nitride to impede the formation of nitrogen polarity. And for the third sample with excessive carbon, those excessive carbon will serve as a mask. And if you grow on top of a mask, you will have those irregular faceted aluminum nitride on the surface, which is also not ideal for device application too. So a proper amount of carbon from the trimethyl aluminum is the key here. So with that knowledge in mind, we have continued to optimize the aluminum polar aluminum nitride grown on sapphire by our MOCVD at KAUST. And currently, if you look at this is the X-ray analysis indicating the material quality. And here is the AFM image indicating the surface roughness. So both material quality and surface roughness are on par with the state-of-the-art results of direct growth of aluminum nitride on planar sapphire. But also you can see we still have a lot of dislocations represented by those darker dots on the surface. And that's something we still have to work on in the future. So since we talk about the growth of high quality aluminum nitride epitaxial layers, then next let's talk about the growth of boron aluminum nitride and boron gallium nitride. Again, it is very similar to that of indium gallium nitride in its early days. They have the issues such as parasitic reaction and phase separation. And for a long time, the boron content of single-phase Woodside boron aluminum nitride was limited at about 1 to 2%, so very low boron compositions. And recently, the boron content was increased to about 12%, but the Woodside phase was rather thin of only 10 nanometer. For the boron gallium nitride, it faces similar challenges. However, the highest boron content was limited at about 7.4% as well. So in our growth studies, we have 3 goals. First is that we have to maintain the monocrystal Woodside structure for device applications. And second, we have to obtain a higher boron content in those materials because we want to understand their properties. And without getting those higher boron content, we will not be able to understand those characteristics. And third, we have to obtain layer with thickness larger or similar to the thickness of interest. For example, a DBR layer has a thickness about 30 to 40 nanometer, and we have to realize thickness higher or equal to that. So without elaborating the growth details of the emulsivity studies, we have demonstrated a state-of-the-art Woodside boron aluminum nitride materials. And here we have the X-rays and XRBS spectrum, both for the crystal quality and composition characterization. And on the right here, we have the thickness versus boron compositions of our results benchmarking with the results from the other groups. As I mentioned earlier, the higher thickness, the larger boron composition, the better, right? So as you can see, we have the largest boron composition, and also all of our samples here have thickness larger than 100 nanometer, which is sufficient for a majority of the applications. But in our group, we are still trying to push the composition higher and push the thickness higher as well. So in nowadays electronics world, most of the compound semiconductor devices are based on a very important structure called heterojunction proposed by Al Farrell and Cromer back in 1959. And also because of that, we have also studied the heterojunction based on the boron 3 nitride materials. And from that, we can then extract crucial heterojunction information, including band offset, strain, defect, and charge for electronic and optical device applications. So one of the interesting property of heterojunction is band alignment. So when you put 2 semiconductors side by side, they will form a heterojunction. And when electron and hole come to the interface of this heterojunction, then we see a barrier or a lower potential, which impede or encourage their movement, right? So the band alignment is probably the most important property of a heterojunction. And in our studies, we have also conducted the research on the heterojunction band alignment of the boron 3 nitride materials. And unlike the conventional indium gallium nitride materials, which always form a type 1 heterojunction, right? We found that interestingly, by adding boron into the aluminum nitride, not only the conduction band minimum, where you have the free electron move up, but also the valence band maximum, where you have the free holes also move up too. So this forms a very interesting type 2 heterojunction, right? So this is very significant because you can then combine the type 2 with type 1 to improve existing devices or to invent new devices. In addition to experimental study, my student has also conducted a DFT calculation of the band alignment for the boron gallium nitride and boron aluminum nitride. And just like the boron aluminum nitride on the left here, the boron gallium nitride also has widespread type 2 opportunities. This is very interesting. When I saw this result, I told my student that this is really a gold mine. The student can really explore and discover numerous opportunities based on the type 2 or the combination between type 2 and type 1 heterojunctions. And when we reported our results, it was noticed by the experts in the field. The compound semiconductor, which is a leading technical media in our field, highlighted our results as the title of the newsletter they send to all around the world. The title was Researchers Discover Unique Boron Aluminum Nitride Properties. So we have also taken advantage of the type 2 heterojunction band alignment for the gallium nitride high power and high speed devices, as well as UV LEDs. So in both scenarios, we notice a considerable improvement of the device performances by having the type 2 heterojunctions. So in addition to the band alignment, the 3-nitride semiconductor has another very interesting property, which is so-called polarization. So polarization of a material basically means the material has an internal electric field inside. And this property actually are not shared by most of the materials we know today. For example, I'm using a table made of wood, and the wood does not have a polarization. Right? And my office has a lot of glasses for windows, and the glasses do not have polarizations. And also, most of the semiconductor do not have polarization. So this is a very unique property. And depending on the crystal planes and depending on the material compositions, there is a different degree of polarization. But basically, the so-called C plane or the polar plane has the strongest polarization, including the spontaneous and the piezoelectric polarization under the strain. And also, most of the commercial devices are built based on the C plane due to significantly lower cost and more mature processing, right? So the investigation of the polarization for C plane 3-nitride is very important. So let's use the heterojunction as an example. Again, a heterojunction is when you put two semiconductor layers, against each other, right? So let's say we have two layers, which are AC nitride and DE nitride, and ACDE can be from the group 3, can be from any of the group 3 elements, such as boron, aluminum, gallium, indium. So when they have formed this heterojunction, there will be a polarization charge at the interface. I call it delta P. And the delta P here is a function of the composition X and Y, as well as epsilon, which is strain of those layers. It is equal to the difference between the spontaneous polarization plus the difference between the piezoelectric polarization under the strain. And this delta P is fundamental for the devices used for 5G communication and power management today. Because without this delta P, there will not be any self-induced two-dimensional electron or two-dimensional hole gas for the gallium nitride transistors. And however, for gallium nitride-based visible LEDs and lasers, people sometimes do not like this delta P because ideally they want the electrons and hole to be at the same place. They shake hands and then they recombine into a photon. But because of the delta P, the electrons and hole are displaced. And this displacement will reduce the probability of electron and hole shaking hands and then recombining into photons, right? So it has pros and cons. So the polarization engineering is actually very, very important and interesting. So since the Nobel laureates Akasaki and Amano Sensei discovered the first p-type gallium nitride, which led to the booming of our field in late 1980s, the research on the 3-nitride polarization has increased dramatically as well. So far, there have been over 100,000 papers about the 3-nitride polarization studies. So it's a very important topic in our field. So in our studies, we have performed the first boron 3-nitride polarization studies for both spontaneous and piezoelectric polarizations. And by combining with that of the Indian aluminum gallium nitride materials, we have built up a 3-nitride polarization framework with different degrees of strains and relaxations. One of our conclusions was cited by Wikipedia on its pyroelectricity webpage. So it says that some of the novel materials, such as boron aluminum nitride and boron gallium nitride, have some very interesting piezoelectric response under certain conditions. And more importantly, for electrical engineers, we can then play with the polarization in a very systematic way for device applications. I would like to use this mechanical toolbox as an analogy here. So if you work on some mechanical tasks, such as repairing your cars or assembling furniture, or doing maintenance on different type of MOCVDs here, you have to select the right tools for specific purposes, right? For example, Allen key, wrenches, screwdriver, saw, and so on. And in this polarization framework, I call it the polarization toolbox. So in this toolbox, we no longer have the mechanical tools, but instead we have all kinds of 3-nitride materials and their combinations, right? And then we can either pick up 1 materials, 2 materials, 3 materials, or a range of materials with great decompositions to do many, many interesting things. For example, we can pick up 1 materials to either minimize or maximize the sensitivity to strain for MEMS, energy harvester, and pyroelectricity. Or we can pick up 2 materials to form a heterojunction, which I mentioned earlier, for diodes and transistor applications. Or we can pick up 3 materials to form a double heterojunction, kind of like a hamburger here, to either minimize or maximize the tunneling probability. Or we can pick up a gradient material to minimize or maximize the 3-dimensional polarization-induced charges for a wide range of applications. So we have also made this polarization toolbox into a software. The applicable substrate include sapphire, gallium nitride, silicon carbide, silicon and gallium oxide. So covering most of the substrate people use for 3-nitrides. And so far there have been hundreds of registered users from over 70 universities, companies, and institutions using our software. And for us, the polarization toolbox is also a massive discovery platform for device structures. Not only has contributed to our type 2 heterojunction study on gallium nitride transistor and LEDs, but also it has led to several of our significant studies, including the first nitrogen polar Greenwich LEDs, the first 3-dimensional heterojunction, and so on. In addition to electronic properties, which I talked about earlier, the optical properties of the boron 3-nitride are very interesting as well. So here we have a 3-dimensional figure showing the lattice parameter, reflow index, and the wavelengths for the boron, aluminum, gallium nitride materials. What is interesting is that we can get the so-called lattice matched heterojunction or super lattice from the boron 3-nitride materials. And this lattice matching is very important for devices, because if you do not have lattice match, or if you have lattice mismatch, such as the studies shown here, your device may accumulate a large degree of strain, which may crack your sample surface and render your device not useful, right? So based on this, we can then construct the super lattice without the lattice mismatch. Then we can grow a very thick super lattice without worrying about the strain accumulated in the device structure. And for instance, if we have the boron gallium nitride and aluminum nitride here, we have 0% lattice mismatch, and then we can achieve a more than 90% reflectivity with 10 pairs and 25 pairs of super lattice, and with a large bandwidth as well. And this is a so-called DBR structure that is in every single semiconductor laser today. And in particular, this DBR will be very useful for applications such as atomic clocks because of the wavelengths in the UVA spectrum. So in the last 20 minutes or 15 minutes or so, I have talked about our research on the emerging boron 3-nitride ultra-wide bandgap semiconductors through the multidisciplinary research. I have shown that our MOCVD research of state-of-the-art boron aluminum nitride has expanded into materials, devices for next generation electronic and optoelectronic devices. So next, I would like to talk about my future research vision and plan. So here is a photo of our MOCVD in operation. So for the future, I would like to double down on the research in the boron 3-nitride semiconductors and enhance our leadership here. So that will include the growth, materials, and physics research for the electronic and optical properties. And then based on that, we can then work on the opto and electronic devices. And there are several angles we can look into for our device studies. Those include polarization, band engineering, and optical engineering. But also we can tap into the power of nanostructures, heterogeneous integrations, and novel fabrication techniques to improve and innovate the device structures. And the devices of specific interest include UV, LEDs, lasers, and photodetectors, as well as high power and high frequency devices. Also, the 3-nitride devices have very high piezoelectric constants, and therefore the piezoelectric sensor are something we are very interested in as well. And to maintain and expand the research in this field, we will seek funding both internally and externally through independent and collaborative works. And hopefully our efforts in this emerging area can contribute to the future development of those crucial applications from space technology, pandemic prevention, electrification, to other very important technology of the human society. So this is one of the research vision. Another research vision I have is to expand into another very interesting and exciting ultra wide bandgap semiconductor. That is the 3 oxide semiconductor. I talked about 3 nitride earlier. So 3 oxide basically is you have group 3 elements, but you combine with oxygen, right? So such as gallium oxide. The 3 oxide also has very large bandgap. This makes them very interesting and promising for power applications, such as shown by the figure right here. They will be more superior compared to silicon carbide, gallium nitride, and silicon for electrification, power generation, and power management. And also another interesting property of the gallium oxide is that it has this low-cost native substrate thanks to easy production compared to the nitride. So expectedly, they will have lower costs for future manufacturing. So when I joined KAUST, I had no experience in 3 oxide research. So we didn't start with that. However, in the last couple of years, we have gradually built up the 3 nitride research capabilities funded by the baseline and available resources on campus. So here are some preliminary studies that we have conducted that I believe will form a good foundation for future expansion into this exciting area. So one of the study is that we have invented a new technique to grow ultra wide bandgap semiconductor. We call it thermal interdiffusion alloy. So in this process, we did not need any precursor or more complex equipment such as the MOCVD, MBE, or PLD. We just need a simple thermal furnace, which just costs about a few $1,000s. And we can then we just have to put a gallium oxide layer on top of sapphire into this furnace. And with annealing, we can form aluminum gallium oxide with different composition and different thickness and different material quality for device applications. And so far, we have demonstrated the state-of-the-art aluminum gallium nitride materials with the largest compositions compared to other more complex techniques. And this result was recently published at Applied Physics Letter. And another study is our works on the flexible gallium oxide devices. We have utilized the PLD system initially from the core lab, and later, thanks to the expert committee, we have got a PLD system from the surplus. And using the PLD system, we have grown gallium oxide, epitaxial gallium oxide on flexible substrate. The growth of epitaxial gallium oxide on flexible substrate is not trivial because most of the flexible substrate have a lower melting point, or they can be easily oxidized. And in the meantime, the ultra wide bandgap semiconductors, such as gallium oxide, prefer a higher temperature for crystallization. But in this study, we have demonstrated first epitaxial gallium oxide, TFT, and the photodetectors. In the pursuit of better ultra wide bandgap semiconductors, our group have also developed ultra wide bandgap MOCVD that is capable of growing 3 nitride and 3 oxide materials. So we have utilized this MOCVD to grow and demonstrate the first 3-phase gallium oxide by MOCVD, including the beta phase, epsilon phase, and alpha phase. And with those preliminary studies, I believe that we will have a good foundation for future expansion into this even more emergent area compared to the 3 nitride. And the future efforts will focus on the development of the state-of-the-art materials and the flexible devices. And so since I talked about the research, let's switch gear and talk about the teaching and other aspects of my career at KAUST. So in terms of teaching, my philosophy is to encourage and inspire active learning for students' enthusiasm and lifelong learning attitude. So since I joined KAUST, I have developed 2 courses. One is ECE 206 and the other one is ECE 390B, which is now called ECE 335. Also, I serve as a substitute teacher for the ECE 208 in 1 semester before. And in 2018, I was very fortunate to be nominated for the Distinguished Teacher Award. And in terms of student advising, I have graduated 1 PhD student, which is heading to as a postdoc at CMU pending the US visa. And I have 10 PhD students in progress in my group. And also I have graduated 7 master students and have 3 master and PhD students in progress. And I have served the number of committees for PhD and master studies. And my students over the years have received some very competitive awards internationally, including the SPIE for Optics and Photonics Education Scholarship. And in terms of postdoc training, I have trained 3 postdocs and 2 are in progress. And the highlight includes one of my postdocs joined USTC, which is a top 3 university in China as a professor. And another one became a senior scientist at SUNY Polytechnic in the US. And in terms of service, I have served on the committees in the program, in the ECE program, also the Applied Physics program, as well as the Academic Council and the Imaging Core Lab. In addition, I have helped the organization of the KAUST National Science Foundation Conference on Electronics and co-organized the KAUST Asia Wide Bandgap Semiconductor Workshop with Professor Poon Oi. And the highlight of my service is the student recruiting and marketing. I have been a founding member of the Photonics Summer Camp. This summer camp over the years has attracted over 90 VSRP students to KAUST. In addition, I have created the UESTC student pipeline, which later was joined by different colleagues at SAMC. This pipeline has attracted more than 30 top-ranking graduate students and over 80 visiting students to KAUST. So here shows the top 8 sources of the current SAMC students, and the number of students from UESTC is about 25 right now. And in addition, I have helped create KAUST marketing in WeChat and Weibo by working with Ma Kong. Those 2 channels are the 2 biggest social medias in China. So hopefully we can continuously to attract better and better students and postdoc and staff and also faculty from China in future. Moreover, I've helped various 3+2 agreements for the international office. And in terms of the external visibility, I have served on the committees of different conferences internationally and regionally. In particular, the IWN is the top conference internationally in our field, and the EMC and so on are the top regional conferences in the US, China, India, and Singapore. And I have served as an associate editor of Photonics Research, which is a journal of OSA since 2018. And I have served as an editorial board member of Journal of Semiconductors since early this year. So in the past, I have received the Harold Manasevich Young Investigator Award named after the inventor of MOCVD from the American Association of Crystal Growth. So let me summarize my talk. So there have been 4 waves of world-changing inorganic semiconductors. I hope you can also agree with me that the ultra-wide bandgap semiconductor, just like the previous 3 waves, will have enormous impacts on the human society for the decades to come. And at KAUST, we have built a leading program in the boron-3 nitride research through multidisciplinary research, including growth, materials, physics, and devices. And for the future, I would like to double down on the research on the boron-3 nitride semiconductor, but also expand into 3 oxide semiconductor, both of which are very exciting areas for future exploration. And finally, if Richard Feynman is still alive, he might well say there is plenty of room at the top. And with that, thank you so much for your attention today, and thank you for the wonderful journey at KAUST.
Thank you very much, Xiaohang, for the presentation. I'll just give a brief summary, and then I'll open the floor for questions from the audience. So again, Xiaohang joined us in 2016 and has been a very strong contributor to the program and to KAUST, as you've seen from his background. Superior above division average, always teaching feedback. On the research side, his work really concentrates on growth, fabrication, and characterization of ultra-wideband semiconductors for optoelectronic and electronic devices. Specifically, the main achievements will be his work on ultra-wideband semiconductor research, that led to fundamental contributions in the area of 3-nitride semiconductor materials. He's been leading a lot of work on MOCVD technology and equipment development, specifically ultra-high temperature MOCVD, which is very critical for 3-nitride and 3-oxide materials that he's planning to look into in the future. So he's paved the path or carved the path towards this capability going forward. His polarization toolbox, as we mentioned, is used throughout 70 universities at the moment. And then lastly, he talked about some of his semiconductor device research as well. So again, the strong publication record, excellent feedback from external reviewers, good mentoring on the students side throughout the past years, and it has only kept improving with time, as well as extensive service and awards over the years. So with that, I would like to open the floor for questions from the audience to Xiaohang. We need one question.
Hello, Professor Lee. I'm Son. Thank you for your interesting presentation. I have two questions.
Sure.
First, boron, as we all know, boron nitride is 2D material. It is very easy to cleavage. I wonder this property affects its device processing and application. For example, during device processing, ultrasound cleaner may make the boron nitride layer separated or cleaved from substrate or other epi layer. How about your opinion?
Yeah, thank you so much for the question. You are right. I mean, the boron nitride is a 2D material, but only with the hexagonal phase, right? Only the HBN is a 2D material. Yeah. Boron nitride have 3 phases. The one we are working on is oocyte phase. So we do not have the problem as the hexagonal boron nitride. I wouldn't say problem that does not have the property with the boron the HBN. The HBN can be easily removed and cleaved. But the oocyte boron nitride has a different structure.
Okay, so you use MOVP to grow oocyte boron nitride, not HBN, right?
Correct.
Okay. So please go page 30. 30,
okay.
Okay.
Yep, go ahead.
So this oocyte boron nitride?
This is oocyte aluminum nitride.
Okay. Oh, okay. Yeah. I have another question is because I read many papers, boron nitride growing by HBN, growing by MOVP has hexagonal ring morphology. So I wonder why your morphology is very smooth. So it's oocyte.
This is aluminum nitride. Again, this is not boron nitride. This particular slide is aluminum nitride. Yeah.
So oocyte boron nitride also have the smooth surface, not the hexagonal ring morphology.
So first of all, we have not grown on the binary oocyte boron nitride, but we have grown the boron aluminum nitride, right? So the boron aluminum nitride is still oocyte. But if you have oocyte boron nitride, it's not going to be hexagonal because oocyte structure is different from hexagonal structure. Right? So, it has a hexagonal basal plane, but it is a little bit more complex compared to the hexagonal, the pure hexagonal structure.
Okay, thank you. Another question: for the case of boron aluminum nitride growth using MOVP, do you also use the positive growth mode?
Depends. I think depends on the type of MOCVD system you have, right? So MOCVD system have different type. One is the so-called closed couple shower head. The other one is the so-called, the high-speed rotation vertical reactor. And they are horizontal reactor. They are, room temperature MOCVD. So different MOCVD will have different conditions. But I guess, you are asking about the condition for the closed couple shower head. And in that
Yes.
case, you might want to use the pulse mode because that MOCVD has a specific configuration.
Okay.
Right.
Okay. Clearly. Thank you.
Thank you. You're welcome. Yeah.
Thank you. We have a question from Omar.
Thank you very much, Xiaohang. I apologize that starting the presentation off at the last minute, I was disengaging from a meeting that ran over. I just wanted to see on the plan. I mean, I see you're approaching things that each in different areas, that each one of those areas has a high level of difficulty. On one hand, there is the material growth and fabrication, and which is really a big challenge on its own. And the other one is on the devices themselves that you can form with these materials. On the device side, are there specific figures of merit or specific milestones that your research is trying to hit that says, okay, if we do that, then we'll get to this kind of performance?
Yeah, thank you for the question. That's a very important question. Yes, different devices certainly have their different figure of merits. For example, like UV LEDs and lasers, then the figure of merit is so-called content efficiency, right? So you always want to hit a higher content efficiency. And also for UV devices, you also want to hit shorter wavelength, right? So because the shorter, the more difficult. So it's like a challenge everybody want to overcome. For power device, it's about output power, output current, and the breakdown voltage. Yeah, certainly by introducing those emergent semiconductor on some of the previous device structures, then we definitely are looking at those figure of merits to see if they can lead to meaningful improvements. Yeah, and apologize, my lights turned off smartly in my office.
Just to Xiaohang, I have a question actually to elaborate a little bit on what Omar was mentioning. Sometimes the national labs in the US, they set this goal for what's happening next to devices, what's happening next to converters, power management, especially on the power management side. It's in our field, it's measured in, for example, the power per inch cubed, for example, of power processing. So is this something that is common in your field? And then how far, for example, are you from pushing pushing the envelope to reach these kind of numbers that are set by typical national labs, for example?
Yeah, so that's right. So you are talking about the roadmaps for different technologies. Yeah, so in our field, we there are different roadmaps. For silicon, for example, the most famous one is the so-called Moore's law. And the Moore's law means you have to double the density of transistor every 18 months. And in our field, we also do have some of those roadmap as well. However, the research in our field is a little bit different from silicon. Because for silicon, the goal is very difficult, but also straightforward. You just have to make the transistor smaller and smaller. In our field, we should not make the device smaller and smaller, because if we make our power device smaller, then it will handle less power. So we want to have the same footprint, but make the device stronger. But sometimes this is not linear. This is not linear. So there is a roadmap, but different groups are trying to use different physics, materials, and different device architectures to hit those goals. In our research, we have currently we are probably the leading team in some of those key figure of merits, right? In terms of shorter wavelengths, and in terms of different different electron and electron hole mobility. But there are other things that we need to work on to catch up with the leading as well, the leading team as well. So, but right now the focus is to try to double down on our leading areas so that we can keep the leadership in those areas. And because in our field, it's about either being the first or being the best, right? So we have tried very hard to be the first in different research area, but we also try hard to try to be the best in certain areas. That will rely on the efforts of the student, postdoc, myself, as well as the core lab equipment and everything.
Thank you. Do we have any other questions from the audience?
One more from me, Shihab.
Sure, go ahead, Omar.
Now, since you're looking also from the question of making and diagnosing and core lab, is there a something from either the characterization or the manufacturing technology that would make a radical impact on how we manufacture these materials?
Can you sorry, can you say your question again?
I don't know. Is there a potential, say, with from either the MOCVD front or from the characterization, so some kind of the services that Core Labs is providing, since you alluded to Core Labs, is there something that could change from the device manufacturing perspective that could be a game changer? What are you watching in terms of the competition even?
Yeah, in terms of the core lab, we have been very satisfied with the core lab. So most of our research, especially when I didn't have a lab, was done in a core lab and also in, for example, in Boone's lab at the beginning. But in terms of core lab nanofabrication, I think it's not just me, but maybe some other faculty colleague who work on fabrication, is that we wish the core lab nanofabrication lab, if it can open longer, that would be great. Because if you look around the world, most of the clean rooms are open 24/7. So, but we have a relatively short opening hours. So a lot of my students and postdoc told me that they really want to work harder, but it's kind of limited by the opening hours of the clean room. Yeah, the other part of the core lab open 24/7. So we some of my students they take advantage of that, but the clean room is something that has relatively shorter hours.
I have another final question, Xiaohang, as well. Just from a technology translation perspective, right? I would love to know. I mean, this seems to be very remote to application to some people. So can you elaborate a little bit on that? I think you have some efforts in that direction. I think it would be nice to just touch upon those somehow and share your thoughts.
Yeah, in general, the overall market of semiconductor is very large, and including silicon, the 3-5, and the compound semiconductors. And our group is working in a narrow field of the area, and this area, but nevertheless, can lead to a lot of the interesting opportunities, including power, frequency, and LEDs and lasers. So in our group, we have, since we work on multiple fronts, but they are connected vertically. And there are something that we believe may be able to, open to more applicable developments. For example, our polarization toolbox that is being used by a lot of the university companies right now can be a potential venue. And also the MOCVD system that we have developed could be a potential way to commercialize, because when we design that, we design it specifically for ultra wide bandgap semiconductor, and the ultra wide bandgap semiconductor MOCVDs are not really commercially available right now, right? So as this field become more and more active, there might be a market for that. But the software does not require a lot of capital investment. But for one MOCVD, I mean, Omar knows this much better than me. The equipment needs a significant investment. So, but right now I have a pretty busy group right now to manage. But in the future, I'll definitely want to learn from you, Shihab, and other colleagues in terms of how to commercialize some of the stuff we are working on.
Before you do, Xiaohang, talk to me.
Yeah, for sure.
I mean, if you invent Coca-Cola, we don't want to patent it. You want to keep it a secret, right? So that it depends what it is you come up with.
Definitely. Thank you so much.
I think if we don't have any other questions, we can wrap up the session.
All right. Thank you very much, everybody, for participating, and thanks, Xiaohang, for a great presentation and for the Q&A. Thanks,
Yeah, thank you so much
for
Omar,
moderating.
Shahab. Yeah, thank you,
Yep.
everybody. Appreciate you.
Thank you.
Yeah.
Good luck. Good luck.
Bye.